In the last class, we were discussing palladium catalyzed carbon nitrogen cross coupling reactions. Essentially, we needed or we can improve the synthesis of amine. Synthesis of amine with aryl ring is indeed challenging, right? So if you want to synthesize a secondary amine with an aryl ring, these are the method of choice where you will have the opportunity to start with a primary amine to get an aryl amine with the secondary amine scaffold. If you are starting with a secondary amine, aryl amine, tertiary amine, you will be able to get. So for instance, you have an aryl halide as the coupling partner and amine as the second coupling partner. So these are the two different coupling partner. One is aryl halide, chloride, bromide, another is the amine. The higher analog of amine one can generate, right? The catalyst is usually the palladium catalyst, but it is not really palladium 0. It starts with palladium 2 as we discussed earlier, but real active species is palladium 0. Often you need a ligand such as phosphine ligand. Okay, and of course a base is required under a suitable solvent. Temperature can usually vary from, let's say, 70 to 100 degrees centigrade. Okay, so in these reactions what's exactly happening? We invariably generate ligand palladium 0 complex starting often from palladium 2 catalyst, and we add a ligand, phosphine based ligand, let's say. One of the problem that we have, this ligand usually which is phosphine based ligand, and in some cases it could be carbene ligand, these ligands need to be small and electron rich for oxidative addition. The ligand has to be small as well as electron rich, because we are trying to incorporate metal inside aryl X bond, right, over here. On the other hand, for reductive elimination, we need the ligand to be big as well as electron deficient. So remember, oxidative addition ligand is small and electron rich. For reductive elimination, because the reduction in the number of coordination side for palladium, and for reductive elimination to happen, you want ligand to be bulky or big so that these two substituent comes out, right? So once again, these are the two criteria which are seemingly opposite. This ligand has to be big and this ligand has to be small, right? So this big ligand, how can in one instant it can be big, but in the same catalytic reaction it has to be small. So this is kind of two opposing factor. As you can see, the ligand has to be small yet big. Ligand has to be electron rich yet electron deficient, right? For one reaction, for a single reaction, how can you, it's not like you can just put two different reaction ligand, one is big, another is small, but then how the metal would know which step to use which? So this is a standard problem. This is a classical problem, I would say, which tells us essentially is the designing of the ligand has to be such that, so that in one case ligand is small, electron rich, the same ligand can act as big and electron deficient in the subsequent reductive elimination step. And this is where we were seeing that these sort of ligand which are essentially the biaryl phosphine ligand, these sort of ligand, any of these ligands are actually working in a electron rich as well as small fashion as well as big fashion. So that is what we were trying to discuss in the last class, where you see at this point the ligand can be giving the palladium in such a orientation so that it stabilize the palladium. Okay, now this ligand in the last slides are electron rich. Electron rich, why? Because you have an alkyl group, you have an alkyl group. On the same time, or at the same time, you see this is going on when you have this oxidative addition going on. But during amine binding, it can come out from the inside. So it was inside here, right? It can come out like this over here, and then during the amine binding, it is giving an opportunity that it is less bulky. Previously it was more bulky, it is now less bulky. Again, for reductive elimination, it can give you a feeling that it is more bulky by swinging in. So what you are seeing here is the fluxional behavior, fluxional ligand. So right now it is in right now. In later on it could be out, completely out, right? So this in and out behavior is helping overall these ligand to be settling between these electron rich as well as small in a way, as well as bulky in some other case. It can give this sort of opportunity. Another important thing is this ligand itself being really bulky, it doesn't allow a second phosphine ligand to come very close to this palladium center. Okay, I repeat. So these ligands, as you have seen, these ligands are much bulkier than triphenyl phosphine type of ligand, right? The cone angle for these ligands are pretty big. Therefore, these ligands do not allow often to have a palladium center where palladium is coordinated with two phosphine ligand. Only one phosphine ligand is attached. Often you will see palladium for phosphine ligand, triphenyl phosphine, four of them, you can see that PPH3, four of them could be there, right? But these ligands are such that in the catalytic cycle or active species, only one ligand can be attached with the metal center. So that also solves many a problem. These phosphine ligand or other ligand which are not that good, this limitation of the other known easy phosphine ligand, simple phosphine ligand, limitation of these things can be overcome by this big bulky phosphine ligand. Okay, moving on, as you have seen in the last class, we are trying to have an opportunity where palladium is sitting on top of the bottom phenyl ring, and then it swings out. Palladium is outside, amine binding, deprotonation happen, and for the reductive elimination, as I was telling, the palladium has to be bulky, or palladium has to have the ligand which is bulky. In this case, phosphine ligand is not that bulky, right? Phosphine is holding the bulk outside, so palladium is not seeing the bulk too much. But when palladium comes back in, then it is in a sterically crowded atmosphere as in here, and that is how the reductive elimination becomes facile. So to sum up this part, I think we have now an excellent ligand in the literature that is commercially available, industrially used all over, especially for the med-chem chemistry. This is an excellent choice for the carbon-nitrogen bond formation reaction. All across the world, these reactions are happening, and these are having similar success storage as, like, let's say, metathesis reaction or other industrially relevant reactions such as Suzuki coupling. This palladium catalyzed CN cross coupling reactions gives us an opportunity to go for a place where oxidative addition into these will be faster by virtue of having this dialkyl ligand, and also the amine binding is also possible, deprotonation also possible, facile, and then reductive elimination. As you have seen, the palladium gives, or the ligand orients in such a way, it brings back the palladium in the groove, so make it look bigger and bulky so that reductive elimination becomes faster. Okay, so this gives rise to another opportunity that if you look at this catalytic cycle, here you will see one of the things that you have as an intermediate is ligand and amine is bound with palladium, right? Now, one of the major problem in this domain is how you generate palladium 2 to palladium 0, right? This step could be problematic. It's not always that tricky. More importantly, this ligand that is out there, these ligands are very, very expensive ligand. Those are very much designed ligand. Sometimes these are more expensive than palladium itself. So what you wanted to have is a ligand which will generate the palladium cleanly, and ligand palladium concentration as well as the formation should be pretty efficient, right? These ligands are good ligand, but this ligand has to work really well. Okay, so if you look at then for this palladium 2 to palladium 0 formation, if you have a pre-catalyst where ligand and this amine are bound together and then they can release this palladium 0, that and then a different reaction with different amine can go on. So this can be a sacrificial catalyst in a way where you will see that that this starting material, which is of not much interest, but with the right ligand, can give a ligand palladium 0, and the product can go out and a new aryl halide and new amine can come in. Okay, by keeping that in mind, what a researcher has designed simply is to take these orthochloro, let's say phenethylamine. Orthochlorophenethylamine upon deprotonation gives this species. Now this species can be commercially available with this ligand, which is the expensive ligand, and under the reaction condition, since an intramolecular carbon nitrogen bond formation is there, it can leave out ligand palladium 0, and this amine can be formed in situ, right? Now this can go out. This is very tiny amount. Of course, this is also very tiny amount. This is also very tiny amount. Overall, this can give a clean formation of ligand palladium 0 species. I hope you understand why it was necessary. So it was necessary because, I would repeat, that palladium 2 precatalyst to palladium 0 formation could be always a problematic step. Okay, these are not reliable states. Always this expensive ligand can be used in huge amount or significant amount for reducing this palladium 2, right? This ligand can usually get oxidized and palladium 2 gets reduced to palladium 0. But these ligands, as I told, are very expensive ligand. You don't want to lose this ligand in any quantity. This is why what you do, you take an intramolecular reaction, which is a sacrificial reaction. You sacrifice a very inexpensive material such as 2-chlorophenethylamine from there in tiny amount, right? So let's say you have 1% of these, then you have 1%, 1 mole percent of that, and then you generate 1 mole percent of ligand palladium 0, right? There is no as such no problem of losing this material. This can happen under the reaction condition where a particular aryl halide and a particular amine you want to couple, right? A desired amine and desired aryl halide you want to couple. What you all do is you purchase this material from market, which comes with this expensive ligand or very well designed, useful and efficient, or the most efficient ligands are attached with it. Now with this, you just go ahead and do the reaction. The first thing in the reaction happens is generation of ligand palladium 0 with 1% formation of this, because you have started with 1 mole percent of this. 1 mole percent of this will form first, then 1 mole percent of this, then 1 mole percent of this. These are the materials you don't need. So from here directly easily you get over there. So from here you directly go over there. This is a sacrificial reagent. Of course, 2-chlorophenethylamine essentially is the sacrificial reagent in this case, but in tiny amount. Now, once you have this ligand palladium 0, then you can go on and do your catalytic cycle, because then you are starting from there. You can go on and do your catalytic cycle. Is it clear, Mamta? Okay, what we are trying to tell here is you sacrifice some material just for clarity, just for getting expensive ligand palladium complex in right shape without wasting any of it, which is going to give you the desired reaction. Okay, now that was the kind of the final important slide for these transformations for this course. I think there are many examples where you will see that palladium catalyzed carbon nitrogen bond formation is used for many important medicine synthesis. This is useful. This is absolutely critical for the success of these reactions. Okay, now let's move on and try to see another important reaction. Before that, let me repeat one more time what we were saying, that all our intention here is to generate ligand palladium 0 species, right? How you generate ligand palladium 0 species is demonstrated over here, where you see that that from palladium 2 you generate palladium 0, where you sacrifice little bit of this, like 1% of this, and you get 1% of that. Fantastic. And then you go on with your life of generating exciting molecule from the palladium catalyzed carbon nitrogen bond formation reactions. Right, let us move on. So we are going to next look at the Heck coupling reactions, which is once again one of the very exciting transformation in the domain of homogeneous catalysis, industrial homogeneous catalysis, or even heterogeneous catalysis. And as I have discussed earlier, this coupling reaction, Heck coupling reaction, is also part of the 2010 Nobel Prize winning one. But most importantly, these are the industrial scale reactions and can be done very, very efficiently. What we see here, we see a less substituted olefin going to a more substituted olefin, in particular substituted often with an aryl group. It could be vinyl group also. So a less substituted olefin is going to a more substituted olefin. The substitution often is happening by an aryl group. So this highlighted R group over here usually is an aryl group. You can take this X as chloro, bromo, iodo, triplet, nonaplet, mesylate. Many different living group can play the role, because ligand palladium 0 is very effective. Suitable ligand palladium 0 is very effective in oxidative addition into many different RX. Okay, now it is really an interesting thought to oxidatively add into triplet like this, which can be done now even with palladium tetrakase and a base such as this triethylamine. What you see is oxidative addition into this aryl triplet goes on, and then this olefin coupling happens to give you the styrene derivative. Okay, 1,2-diaryl styrene derivative. Okay, what you have over here is a very little substituted olefin like styrene, monosubstituted olefin give you disubstituted, one substitution here, another substitution here, disubstituted olefin you get, which is again very, very exciting transformation. The way these reactions works simply is you start with ligand palladium 0. Okay, you start with ligand palladium 0. In the last 5 minutes I was discussing how to generate ligand palladium 0. This could be similar way we can generate ligand palladium 0, or any other method of choice can also be used. But this ligand palladium 0 synthesis is quite important. This palladium 0 synthesis, it could be one ligand or two ligand depending on the bulkness of the ligand. As I was saying, the monoaryl biphenyl phosphine ligands, those particularly the Buchwald type of ligands, are quite important for many palladium catalyzed cross coupling reactions. But those ligands usually provide only single opportunity to coordinate. But anyway, overall, what we can see that oxidative addition into the CBr bond, which is quite important to do. That's what has happened. As you see, these are the new two bond that is formed. This is oxidative addition, and then olefin coordinates with it. And this is, you can see the nucleophilic center, this attacks over there, and then that add to the palladium. So you all usually have a carbon carbon bond formation right over here, and the palladium is at the beta position. Now this beta position palladium can undergo beta hydride elimination as is shown in here, and overall it can take this proton from this highlighted edge, and it can give you the in this case ethyl cinnamoid or methyl cinnamate ester, right? Now this is a very simple reaction, and it works quite efficiently for these sort of reactions. Okay, what are we looking at? We are looking at aryl halide. It could be chloride, bromide, iodide, or it could be triplet, nonaflet, mesylate, and then palladium enters into the CX bond. Subsequently, olefin coordination, insertion, and beta hydride elimination gives you the opportunity to generate the acrylate in this case. So a less substituted olefin such as this, in this case methyl acrylate, gives you methyl benzoate, so the disubstituted olefin. So the monosubstituted olefin that you start over here, monosubstituted olefin gives you the disubstituted olefin. The ligands usually, for simple reaction, it could be even simple ligand, but if you want to get excellent yields and very little time, less temperature and everything, if you want a very very efficient reaction, of course those phosphine ligand, the bulky phosphine ligand, and highly designed one, and highly useful ones, as you have seen in other cases. Many different other ligands are also been synthesized. It need not be phosphine based. Other variants of the ligand for palladium can also be found. Of course, almost any phosphine ligand would give this sort of Heck reaction, but it would be important to note that if the reactions is not facile, a lot of side reactions can happen, and the loading of palladium has to be high. The idea of these reactions, or the major objective for these reactions, simply is how to reduce the loading. It's not, the major idea is not to do the reaction anyhow. This reaction will happen. These are excellent reactions, will definitely happen. But for all these palladium carbon nitrogen bond formation and palladium carbon carbon bond formation, in particular Heck reaction over here, it's not the matter of making the reaction happen. It's like how little palladium you can use, how quickly you can do the reaction, of how greener the reaction condition can be. Can you do it even base free condition? Can you do it at room temperature? Can you do it with tiny amount of palladium? Like, let's say, jokingly I was saying it's like a homeopathic amount of palladium, right? These reactions occurs, but industry, when they are going to use in 100 kg scale, Even if it is 1 mole % palladium, that's a lot of palladium. It has to be, let's say, 0.0001 mole % of palladium. That's something industry would love. So that means you have to use a system which is very, very sensitive and important, as well as working efficiently for a given purpose, right? So you can do, of course, always end up doing the substrate specific optimization to find out which ligand or what type of reaction condition is best and how quickly perhaps you can do these reactions, right? But nonetheless, we need to have these reactions done very, very quickly and efficiently. Okay, so this brings to an opportunity to discuss these reactions in many other setup. There are many exciting avenues where this carbon halogen bond can be activated and can be inserted, okay, and then an important reaction can be really performed. For instance, as you can see here, this is an exciting reaction. It's a simple reaction. As you see, oxidative addition can happen in here, and after that, of course, you can get the isomerization of this double bond, or you can have the oxidative addition, then the oxidatively addition intermediate can go and add to this, okay, and palladium can come over there, and then bond isomerization would lead to this N-acyl protected indole type of derivative. So the palladium first can come over here, okay. That's the new bond, that is going to form. So you can get essentially as a molecule to first step to get a situation where you have N-acetyl version of the compound with the palladium in here, right? And then this CO2Me, this H can go out, and this can go out, so the double bond can be here, and then insertion into this further, and palladium over here can take place, or the double bond isomerization simply gives you the opportunity to further isomerize this double bond to give you the indole product, which is, I thought, is quite exciting, right? Another exciting transformation could be this aryl, this cyclohexanone substrate with OTF over there, and this position being substituted. You can undergo oxidative addition at this position, and then oxidatively added intermediate can attack over there. So this, you are creating this stereogenic center over there, and then the palladium can come over here, which can attack over there, and palladium can come there. Subsequent beta hydride elimination can give you this intermediate, right? So I think that is again a very, very exciting thing to know, that this sort of you can say the cascade type of reaction can also be feasible by this reaction. So in this intramolecular cyclization or spiral ring formation, and then subsequent palladiation can happen, okay. So you can imagine after this reaction, palladium would have been over here, and of course this double bond is not there, and then from there the hydrogen that is present, that can give you the H palladated intermediate to give this exciting molecule, right? Okay, so these reactions, as the title says, these are intramolecular Heck reaction, which can be quite exciting at a number of cases. There are many asymmetric variants of these reactions, intramolecular Heck reaction, because the aryl halide and the olefin are within one molecule, and this works best. Okay, almost nothing can beat this reaction because oxidative addition is very facile, usually with a modern day phosphine ligand, biaryl phosphine ligand. Oxidative addition will be very, very facile with a very little palladium loading, and then once oxidative addition occurs, it can then go on to form the olefin insertion product, olefin interaction, and the insertion product subsequently beta hydride elimination and series of beta hydride elimination, basically isomerization, can give you this product formation, right? And as I was telling, that's the same mechanism as we have discussed in here, exactly same mechanism go on and on and on and on, right? So what we are seeing over here is an interesting thing where it is not an halide anymore, and that is again interesting because you can have the corresponding OH. From there we can synthesize the OTF, right? But more importantly, once you are here, it gives you an opportunity to attack this carbon center, and that center can attack over here, and the end game will be the palladation at the terminal position. So palladium would be at the end of this chain, wherein you see that all the great things can be worked out with this procedure, right? I think that's fundamentally very important, and it works with quite high yield and efficiency. Okay, so if you may be wondering how good are these reactions, maybe indirectly you can get this answer from this. There are many report or many news art or the article, but this is a current organic synthesis paper in 2010, which essentially says that this year the number of papers was 5900, and that means in every year, or for that year at least, particularly 11% gain on previous year. So that indirectly tells how important these sort of reactions are and how valuable this contribution has been. Of course, at the beginning of these sort of studies, the reaction mechanism was not well understood. It took some time, but eventually it was really understood that it is possible to do these sort of reactions, right? So what we all have here is an exciting transformations from an unsubstituted or less substituted olefin to a more substituted product. So this is only mono-substituted, you get di-substituted product, and these reactions are excellent. It working out quite efficiently for these reactions, and works really beautifully. And you see, even in 1 year, 92 patents are filed worldwide. You can imagine these reactions were getting developed from 70s, 80s, 90s, all the way to 2000s and 10s. Still, these many patents are being filed. I think this got to be important. The way the molecules are prepared by this transformation got to be utilized, got to be important both in industry as well as academic setup. Okay. So that is what we are seeing again and again, just to give you an idea how important these reactions has been. Now these are Novartis product. So Novartis product, this is an herbicide, this is in the market, and prosulfuron, it can be synthesized by utilizing this Heck reaction. As you can imagine, this part you can have an olefin over here to start with, and the reduction would give you, so the aryl bromide can be over here and the olefin can be double bond CF3, right? So that's a very important reaction, aryl bromide, or you can even think of doing this reaction by I would say CH bond activation reactions, right? That would be quite useful to do these reaction by CH activation reactions, right? Now that could be an any day they add important transformations, okay, to do these reactions by CH activation, okay, and I would say that's a very neat reactions for these sort of cases. Okay, now over here you see this is again an important entity. This is single layer, and it's from Merck. It is an asthma drug. You can either see that it can aryl bromide can be over here and the olefin can be over there. Okay, alternatively you can have olefin on this side, so you can have the bromine over here and the olefin on this side. So either this way or that way, both the way you can cut this. So if it is an olefin with R group here, let's say R1 and R2, you can cut this either here as an aryl group. Since R1 and R2 are all aryl group, you can cut either in here or you can cut in either in here, which I thought would be fascinating. Okay, and then of course naproxen and anti-inflammatory drug can be for the migraines. There is this elytriptan, which is a Pfizer drug, can also be synthesized. One can imagine that this could be a double bond, okay, and this CH bond of indole moiety can be a CH bond, or in this particularly in this case it can be bromo over here, and this olefin can be taken out and synthesized efficiently. Right. So what you all see that these are among the very important drugs that is in the market from, let's say, 4 different company here. Novartis, Merck, Pfizer, and Albemarle. Albemarle. All these 4 different drugs of completely 4 different types. But the olefination, since it's the backbone formation for this molecule, can also be carried out by utilizing these simple methods. Okay, so in all these cases you would see that one would need very efficient reaction mechanism as well as very efficient transformation for these to be industrially relevant. Okay, so what we have is an example, representative example from 4 different companies here. There are many such examples from industry where Heck reaction is actually used. These are some representative examples again. In these cases, industrial synthesis of pharmaceuticals, different things, as you can see, this acrylonitrile, in one of the cases it can be generated from here. This acrylonitrile can be taken with an bromo, let's say over here, pretty easily, and can give this product rilpivirine from these reactions quite efficiently, which is a remarkable reaction of its type. Similarly, the TCM20 derivatives by Pfizer can also be synthesized by utilizing the Heck coupling reactions. Okay, so these are all very useful compound, are available in market or in medicinal form. There is an exciting transformation. There could be an opportunity to generate even the vinylation reaction in an asymmetric fashion. For instance, in these cases you have this furan derivative with an olefin in there. Now these olefin are quite exciting substrate because you will have an opportunity to generate a stereo center in there. What is happening over there, that after oxidative addition, this palladium will add into this carbon center, and then palladium can come over there in this carbon center. Subsequently, the oxidative addition, let me draw it. So you have an aryl group in here. Okay, so this is the stereogenic center. Formation of this carbon-carbon bond will be controlled by any of these ligand. As you can see, E can vary 96%, 91%, even up to a very low 20% in some of the not so good ligand. Now the palladium comes in here. Subsequently, this is the proton which gets roll over for this, and then palladium comes in from here. So next step would be palladium will be here, once it is goes out in H palladium form, once it is go down on H palladium form, then again it can go out and form an intermediate. So let me draw the intermediate in here. Then it forms an intermediate where palladium is sitting there and aryl group is sitting here, right? And subsequently this proton, which is the acidic one, will now be giving away for this center. So overall, as you see, the double bond which was here, it end up staying coming in this side. I hope you understood what we tried to do here. The isomerization of the double bond that is happening quite again and again and again leads to a very exciting product formation. In these cases, we get very high level of EE with a suitable ligand. Okay, so with this ligand, we get a very high levels of enantiomer selectivity. For example, as you can see in here, as I explained, that oxidative addition happens and then this carbon attack at this center, palladium comes in this position, and from there on beta hydride elimination can go on from here. H palladium intermediate can be coming out, and subsequently palladium can insert beta migratory insertion. So what happens at after certain point, palladium is over here and aryl group over here, and it was palladium, H palladium intermediate sitting there, which was generated previously. Now then the beta migratory insertion will see an intermediate where palladium is over here, right? And then beta hydride elimination from there would lead to the product formation that you have seen in here. That is, I would say, quite exciting, because this is the same intermediate as this, right? This is then undergo further beta migratory insertion to give you this product formation, and that is the product which is forming in major quantity. As you can see, the other product which is R, 28%, 10%, and 42% it is forming, which is pretty okay for these sort of reactions. Okay, so we have seen the limitations of this reaction to some extent. Phosphine ligands attached to the palladium catalysts can be toxic and expensive. That is true for many other cross-coupling reactions over there. Palladium catalyst will not be available at the end of catalytic cycle and needs an effective procedure to recycle the catalyst, and that is also correct. So which we need indeed is an exciting transformations for doing these sort of reactions, and we will be end up doing these transformations quite efficiently. So let me quickly summarize what we have discussed in the Heck reaction. Heck reaction gives an opportunity to create from a less substituted reaction, less substituted olefin to a more substituted olefin. It was mono substituted olefin you started with, and the end you get di-substituted olefin. From a styrene, you get the di-substituted olefin like this, 1,2-diaryl alkene you generate. Okay, so these are called stilbene molecule, right? So stilbene type of molecule is getting generated from this process. Quite importantly, also what we see here is the reaction mechanism is similar to what we have seen before. So oxidative addition into the C palladium bond and subsequently olefin binding at this palladium center, which is happening, and the nucleophilic attack on the olefin C palladation happens at the beta position, and from there beta position hydride elimination can give you an intermediate which is olefin coordinated. This olefin coordinated intermediate then go on to have this the disubstituted olefin in this case. You started with a monosubstituted olefin, you end up getting a disubstituted olefin. As we discussed, there could be an exciting intramolecular version of this reaction, which is intramolecular Heck reaction, where both the olefin as well as bromine are in one molecule, and subsequently this oxidative addition happens in here. Oxidative addition happens in the severe bond in here, and this attacks in there, and that leaves the palladium here. Subsequent beta migratory insertion and beta migratory beta hydride elimination and beta migratory insertion leads to the rearrangement where double bond ends up being in the ring, which is basically unprotected indole formation. We have seen there are many tons of thousands of reactions that we can see by utilizing this method. In this example, as I was trying to say, oxidative addition happens here, this attacks over there, and that attacks in this carbon center, and then palladiation happens at the terminal position. Beta hydride elimination gives you the product as you see in here. These reactions are quite important. As you see, it's just a simple data from current organic synthesis, which is essentially showing that the activities are quite high, 5,900 papers in a year, and a jump of 11%, nearly 92 patent in the year of 2009-10 or in that period, which is quite exciting for any reaction like these, and these are truly industrially relevant reactions. So what are the problems here one would face? One would face the homocoupling of the aryl halide. That is a traditional problem. Proto-deboration. So for example, if you are starting with bromobenzene, this is the problem for all sorts of cross-coupling reactions, so to speak. If you start with bromobenzene, if the reaction is not good, you can get benzene, right? Because proto-deboration or proto-dehalogenation can happen. At the same time, oxidative addition can lead to the homocoupling product. That means over these product can also be forming quite a lot. So not only benzene, from here you can get the biphenyl as well. Of course, other problem could be, this is one type of problem. Other problem could be if your main reaction is not working, this olefin can also homocouple to give you an conjugated diene like this homocoupling, right? I think that could also be not so great or exciting, right? This cannot be way too exciting as well. Right, so this is going to be quite important and exciting given the transformation, that these are the transformation which is occurring quite well. The side product, as I was saying, the protonation of the CX bond, that means it's called dehalogenation reactions, can give you the reduced form of the benzene ring, whereas homocoupling can always be on the card, and homocoupling of the olefin can also be happening. Often the di-olefination are not of a problem, but nowadays with the different reaction condition, one can expect the dihalogenation as well. We have seen many different examples. These are just a simple example showing that how the olefination reaction may be happening from different drug molecule, different best-selling molecule, or the most demanding compound which has clear usage in the industry as well as in human life, can be prepared by utilizing these techniques. There are many examples. These are just a few examples that we were discussing. In this case, this reaction product formation is quite unique, and I would say it was pretty exciting to see such transformation where we see that a simple olefin such as the cyclic one with a heteroatom alpha to it is dictating the term of the reaction eventually to give a product where double bond is isomerized on this side, not on this side, and making these centers stereogenic, and subsequent reaction can happen from there. And this is the product where we see that that this is the ligand which we see that will give you the best reaction of all. Okay, so that's it for today. We will meet again in the next class. Till then, thank you very much. If you have any question, I can try to answer right now. Hi, any question? Yes, Amitabh, go
Yeah,
ahead.
sir, as we discussed in the main in the this hack reaction, we
Mhm.
are just increasing the substitution, like
Yes.
less substituted to high substituted. So it
Mhm.
doesn't matter, like, okay, it should be the aromatic higher substitution or aliphatic higher substitution. It doesn't matter.
Well, aromatics oxidative addition will be a little bit easier, but aliphatic one you need to have it usually. Yeah, it is also possible. You know, it's not like it's not possible. It's possible. Usually, people are looking for the aromatic one. Aliphatic one usually sometimes the radical mechanism comes into picture, right? Let's say
Yeah.
you have chloroalkane like this, so that radical mechanism can come into picture. But it is also possible not only aromatic, these sort of vinylic compound can also be giving you the product. Okay, many vinylic halide are also there that can be giving the product. Okay.
Okay. In some cases, we are using the triphenyl phosphine
Mhm.
quaternary, or some time we are using DBA instead of
Oh,
triphenyl
okay.
phosphine. So it's just only we are taking as per the reaction condition, or it's like, okay, no, in this how we standardize this palladium
Yeah,
catalyst.
that's a very good question. First of all, let me tell you that dibenzyl acetone, which is over here, DBA, dibenzyl acetone, triphenyl phosphine, these are not really an excellent ligand. Okay, this, for example, dibenzyl acetone is not really a great ligand for this sort of reaction. But you know, palladium DBA is commercially available, PD2 DBA3 or PDDBA2. If a reaction can be done with DBA as the ligand without adding any phosphine ligand, sometimes people prefer to do that. But industrially, most often you will not see that these are the ligands people are using. People will be using the expensive ligand because they are very efficient. For example, for a simple reaction, you may require 10% palladium with palladium DBA or even palladium tetrakis. But if you take those expensive ligand that I was discussing in the context of palladium catalyzed carbon nitrogen bond formation, you may get 0.001% palladium, right? So it's not the matter. I think one of the most important thing is to note that it's not whether you can do the reaction or not. Often almost any palladium will give you the reaction, any phosphine ligand, any sort of any, even lot of amine based ligand, almost many ligand, or I would say any ligand will give you the product. But here we are not talking about the product formation. Main important thing is how low the palladium loading can be. Palladium, how little palladium catalyst you can use, right? That will dictate the utility of it. Because let's say you want to synthesize a medicine by utilizing this. Now if you use 10% palladium, lot of palladium will be left in your final compound as an impurity. By column chromatography or other treatment, removal of this metal will not be possible. So for example, in those cases, or most of the cases, if it is industry is going to use for the medicine or any purpose, I would say very rarely they would take palladium phosphine complex, because there is another better ligand out there which would be much superior than phosphine ligand. Forget about DBA, definitely DBA is not a good ligand. But in academic lab, I mean, in research laboratory, it is okay sometime to use these ligand, because you are not going to take this medicine for consumption, right? You are just trying to see whether reaction occurs or not, right? So for the academic purposes, publication purposes, sometimes people use many different type of ligands, right? But I think the major focus should be to identify the best reaction condition, best ligand, best everything for a given transformation, if you are talking in terms of industrial scale. Does that answer your question?
Yeah, it's fine. Thank you, sir.
Thank you. Thank you. Do you have any other question?
No, it's fine.
Okay. If not, we are concluding here today. And then we will meet in the next class. I will send an email, and we'll meet soon. Okay. So
Sure.
I'm going to stop recording now.
Okay.
Okay.